the packing. So I hope you all did it. And I will just give you here the solution. And if that's not what you find, you can ask me maybe later or your colleague who got the correct result. So for the packing, the packing fraction was defined as the volume occupied by one sphere, so the sphere volume times by the total volume per atom. So for the simple cubic lattice, the packing fraction is pi over 6. It's what you got? For the BCC, the packing fraction is a square root of 3 divided by 8 pi. And for the FCC, the packing fraction is pi over 3 times the square root of 2. That's what you get. Okay. So one has that the packing fraction of the FCC is larger than that of the BCC, which is larger than that of the simple cubic. This is, well, the numbers are around, this is about 0.52. This is about, sorry, yes, 0.52. This is about 0.68. And this is about 0.74. So this larger than this, larger than this. And this is consistent also with the coordination number of these lattices and the fact that the FCC is the most, one of the most packed structure lattice. Okay, so this is for the packing. And now, today I'm going to continue with crystal structure and Bravais lattices and introduce a new concept, which is that of the unit cell. So the unit cell, and this is for a given Bravais lattice or a given Bravais lattice. It requires it's related to a given Bravais lattice. So the definition of the unit cell is a region of space which, when translated by all Bravais lattice vectors, fills the whole space, and this without overlap. So a region of space which, when translated by all Bravais lattice vectors, fills the whole space without overlap. Okay, so this is the definition, and now we will look at some example. The simplest to draw is in 2 dimensions. So let's consider the case of a 2-dimensional square lattice. So the square lattice, Bravais lattice. So, okay, maybe I will continue on this side. So the square lattice, I have therefore, I consider primitive vectors A1 and A2 having the same length and orthogonal, and my square lattice is here. Points of my square lattice, and so on. You can continue up to infinity. Okay, so this is the square lattice. So the Bravais lattice vector are of the type R is equal to N1 A1 plus N2 A2 with for all N1 and N2 integers. So these are the Bravais lattice vectors, and an example of a unit cell would be, for instance, the cell that I would obtain by considering this region. Actually, I would include this side and this side, but not this side and this side, in order not to have overlap. So if I consider this region and I translate it by all Bravais lattice, I fill the whole space without overlap. So this is an example of a unit cell. And actually, I can define this region that would be the example of a unit cell would correspond to the region defined by all points P, such that P is equal to x1 A1 plus x2 A2 for x1 and x2 between 0 and 1. I'm not including one of the two bonds. So the P defined by this corresponds to this shaded region, which is an example of a unit cell. But of course, as we have seen, the primitive vectors of a Bravais lattice are not unique. The set of primitive vectors is not unique. There is an infinite choice. And if I choose another example of primitive vectors, for instance, if I was taking A1 like this and A2 prime like this, which would be also a very good choice of primitive vector that would generate the same Bravais lattice. Then, if I use this to define the region, a region of unit cell, I would obtain this region here of space, which would also be a unit cell. Namely, if I translate this by any Bravais lattice vector, I obtain the full space and without overlap. So this is also a perfectly good choice of unit cell. And there is an infinite choice of a number of unit cells that one can obtain, in particular from this using just two primitive vector for the Bravais lattice, and one has there an infinite choice. In addition, if I consider, for instance, something like this, so including, I can either include only one of the sides or half of each sides. That would work as well. So here, let's see, I consider only one of the sides, the bottom one and this side. So would this, for instance, also be a unit cell or not?
Yes.
Yes.
It will be a unit cell, but not a primitive unit cell.
No. It's
for a Bravais lattice.
For a Bravais lattice, it fulfills completely the definition here, and it's also a unit cell. So actually, this would also be a unit cell according to this definition. But of course, it's not very practical, hard to define mathematically, and I mean, they can be very complicated, very simple, or relatively simple, but there is an infinite number of unit cells that one can have. Now, there is something in common, of course. There is a one-to-one correspondence between the volume, or in two dimensions, the surface of the unit cell and each point of the Bravais lattice. So this is some invariant, that is the volume of the unit cell remains the same. But apart from that, the shape, the length in one direction, there is a lot of possibilities. And, yeah. Okay, so this is for the unit cell of a Bravais lattice. So now there is some particular choice of unit cell, which is especially convenient and symmetric, and this is what is called the Wigner-Seitz cell. So there is one special unit cell that we will introduce and use also later in the course, which is called the Wigner-Seitz cell. So the Wigner-Seitz cell is defined as the region of space that is closer to a given lattice point than to any other lattice point. So the definition of the Wigner-side cell is the region of space that is closer to a given lattice point than to any other lattice point. So this is the definition of the Wigner-side cell. So in my example of a square lattice, using this, that is, I'm looking, I consider as reference point this point, this is the origin in my Bravais lattice here, and I want the region of space that is closer to that point than to any other point of the Bravais lattice. So if I want to construct this, I use my reference point and I look at the neighbors. So I have this point, and my region must be closer to this point than to this point. So I will introduce the bisecting line here, and I know, according to this definition, that my region must be on this side, on the left side of the bisecting line between the point A here and B here. Okay? So I know my region must be on this side of the bisecting line. So, yes?
I beg that you repeat.
Excuse me?
I beg that you repeat. Please repeat.
Okay. So I want to construct the Wigner-side cell for the square lattice. Okay. Now, the Wigner-side cell is a region of space that is closer to a given lattice point. So I consider as lattice point this one, which I call the origin, than to any other lattice point. So the region must be closer to this point than to this point, and the same for all other neighbors. So I consider first this point, this neighbor. And I know my region of space must be closer to this point than to this point. So for sure, my region of space must be on this side of the bisecting line. Okay? So I already know that my region must be on this side. Now, if I look at the second, another neighbor here, the same argument holds. So I draw the bisecting line between these 2 points, perpendicular to the segment of this between these 2 points, the middle, passing through the middle region. And I know that my region, Wigner-side cell, must be on this side of the bisecting line, because the region must be closer to this point than to this point. So I know it must be on this side. And the same if I consider this neighbor. So again, I have the segment between these 2 points. I construct the bisecting line, and I know that my region must be on this side, so that the points are closer to this point and to this point in the region of the Wigner-side cell. So this gives me this. And then I consider this other neighbor here on bottom, and the same argument holds. That is, I construct the bisecting line, and my region must be on the upper part here. So it must be here. So basically, from there, I obtain a square. And if I consider some other neighbors, so the second nearest neighbors, which would be here, okay, I could also construct the bisecting line but it would be here. And in any case, my region is already on this side of the bisecting line. So looking at other neighbors, second nearest neighbor, doesn't restrict more my region. So I have my full my full Wigner-side cell here in green, which is a square centered at the origin around my reference point for that Wigner-side cell. So this is the Wigner-side cell of the square lattice. It is a square centered about the reference point when it's considered. So this Wigner-side cell has three properties which are interesting and make it special. Well, the first one is just that it is a unit cell. I will show it more in general in a minute. So it is a unit cell. Secondly, it does not depend on the choice of the primitive vectors. It does not depend on the choice of the primitive vectors, and it has the full symmetry of the Bravais lattice. Okay, so let's look at this property one at a time. First, it is a unit cell. So, in general, to show that it is a unit cell, one has to show that any point in space can be obtained by translating, or is included by translating the Wigner-side cell. That any point can be reached by translating the Wigner-side cell, or the unit cell. So if I consider a point here in anywhere in space, to show that it can be reached by translating by lattice vector the original Wigner-side cell, I use the following argument. This point is closer to a given lattice vector than to any other lattice vector in space. It is closer to a lattice point than to any other lattice point in space, okay? So it belongs to the Wigner-side cell of this lattice point. And therefore, by translational invariance of the Bravais lattice, by using the vector that connects two lattice points, I can translate this Wigner-side cell into the Wigner-side cell around any point of my lattice, and in particular around the point centered at the origin. So basically, by translating by the vector, that Bravais lattice vector that relates these 2 points, I can translate the point here into the Wigner-side cell around the origin. And therefore, any point in space can be covered by translating the Wigner-side cell to the by a Bravais lattice vector that corresponds to the Wigner side cell that in which this point was included. Okay? All right. Any point can be reached because any point in space is closer to a given Bravais lattice point, and therefore it belongs to its Wigner side cell. And by translation of the variance of the Bravais lattice, I can bring it by translating by this Bravais lattice vector that connects these two lattice points. I can bring this point into the Wigner side cell around the origin. And this I can do for any point in space, and therefore I can reach any point in space by translating this unit cell by Bravais lattice vector. Okay? So this shows that any points in space can be reached, and in addition there is no overlap because any point is closer to a unique Bravais lattice point in space and therefore belongs to its Wigner side cell, and there is no overlap.
The recipe for Wigner side cell seems to be in a little bit ambiguity with the definition. Because
Why?
what about the boundary points?
Okay, the boundary point is a little bit tricky, but let's say for anything that is at the boundary, we put a factor 1/2. And therefore, we are clean. It's, well, okay, we are not mathematicians, we are physicists.
Actually, ma'am, I was like in this case, like
Yes.
in the previous time, like two of the border stayed with this point and two of the border stayed with the points above
Okay,
them.
so the points on
But if we
the
do that,
border,
then-
you split them by half, and you have 1/2. I mean, it's just at the border that you have this ambiguity, but anything at the border, you just put a factor 1/2, and you consider them. I mean, half on this side and half on the other side. Yes, there is just the boundary that is a limit, but if you consider this factor 1/2, then you are okay in the sense each time you can reach it twice, but you had a factor 1/2, so you. In the end, you reach
Okay,
it.
well, counting it, we
Yes.
factor is by 1/2 and each border will be counted 2 times.
Yes.
So, okay.
Yeah, yeah. Okay, so it is a unit cell that is any point can be reached, and there is no overlap because any point in space belongs to the Wigner side cell of a unique point is in the lattice, is closer to the unit cell of your unit point in the Bravais lattice, except at the boundary we also still issue with a factor 1/2. Okay, so it is a unit cell. It doesn't depend on the choice of the primitive lattice vector. This is obvious from the definition. There is no mention of primitive vector. And it has the full symmetry of the Bravais lattice, which means that the Wigner side cell transforms into itself if one applies any symmetry operation about the reference point, lattice point, that transforms the Bravais lattice into itself. So in particular, all rotation about this point that transforms the Bravais lattice into itself transform also the Wigner side cell into itself. So if I apply a rotation of 90 degrees, I transform the Bravais lattice vector into itself. If I rotate it around this point, and I also transform the Wigner side cell into itself. So, and this property holds for any of the symmetry operation that transforms the Bravais lattice vector into itself, the point group, the symmetry operation of the point group that is centered on this point. This includes also the reflection. For instance, I have a reflection plane here, a mirror plane, which transforms the Bravais lattice vector into itself. This point goes into this one, and this one into this one, and this gives me the same Bravais lattice vector, and also the Wigner-side cell transform into itself. So the Wigner-side cell has the full symmetry of the Bravais lattice, the full point group symmetry of the Bravais lattice. Okay, you see it? Okay, so these are the three properties of the Wigner-side cell, and it is a unique object that is well defined and has good symmetry property, which is a very simple object. So this is the Wigner-side cell. Now I wanted to give you another example of Wigner-side cell in 2 dimensions, which is that of the triangular lattice. So let's look at the Wigner-side cell of the triangular lattice. So second example would be again in 2 dimensions, the triangular lattice. So triangular lattice is like this. Okay, so this would be so these are points of my triangular lattice, and if I want to construct the Wigner-side cell using this definition, so I consider I want the Wigner-side cell around this point, this reference point of the Bravais lattice. So I look at the nearest neighbors, for instance this one. I construct the bisecting line perpendicular to this segment between the 2 points, and I know that my Wigner-side cell should be on this side of the bisecting line, because it corresponds to the point in space that are closer to this point than to this point. So this is the first segment that I can draw. Then I consider another neighbor, for instance this one of my reference point. Again, I construct the bisecting line, and this gives me, this is the bisecting line, and I know that my region should be on this side of the bisecting line to be closer to my reference point, and so on. So this is another neighbor. I want the region closer to this point, so my bisecting line will give me this region on this side. Again, if I consider this point as neighbor, bisecting line and the region is here. This point as neighbor, the bisecting line is here, and I have to be on this side of the region. And finally, I have this neighbor, and the bisecting line is here, and this gives me the Wigner side cell. I have 6 sides, which corresponds to the 6 bisecting line to the 6 nearest neighbor, and my Wigner side cell is this object, which is a hexagon. So the Wigner side cell of the triangular lattice is an hexagon. Inside of an hexagon. Okay?
Yes.
And again, this has the full symmetry. Well, obviously, if one looks at the second nearest neighbor, the bisecting line is well outside the Wigner side cell, and it doesn't restrict more my region. So this is indeed, it's enough in this case to look just at the first nearest neighbor, like in the square lattice. It's not always like this, but for these 2 examples, it's enough to look just at the first nearest neighbor of the lattice point. Okay, so this has also the full symmetry of the Bravais lattice, in particular the rotation of 60 degrees around this point that transform the Bravais lattice, all the points into, the Bravais lattice into itself, also transform the Wigner side cell into itself, and the same for the reflection. I have a mirror plane here, which transform my Bravais lattice into itself, and it also transforms the Wigner side cell into itself. So also here one can see it has the property.
Maybe I need some explanation for the unit cell.
The what?
A unit cell.
Yes.
What is the best definition, description?
Best is a little bit, it depends for what. This is okay, the definition is simple. It has very convenient properties. To have the full symmetry of the Bravais lattice is a nice feature. It doesn't depend on the choice of the primitive vector, which is very convenient because one doesn't need to, it's independent on that, and therefore it has a uniqueness. To some extent, this is a very good choice. But sometimes for 3D lattices, it's actually simpler, or the conventional cell is not the unit cell of the Bravais lattice. That is, okay, let's take the example I will show you in a few minutes. In 3 dimensions, you have the Bcc lattice, for instance, and Fcc lattice. So these are Bravais lattices. They can be seen either, the atomic structure can be seen either as a cubic lattice with 2 or 4 atoms in the unit cell, or as a Bravais lattice with 1 atom in the unit cell. But if one looks at the primitive cell of the Fcc lattice, it's a complicated object. Instead, the primitive cell of the cubic lattice is a simple cube, and it's easier to see and to... So, Wigner side cell is the best when you have a given Bravais lattice like Fcc, and you want its unit cell, so the cell with one atom in the cell. Then the Wigner-Seitz cell is very good. But sometimes one prefers to have a bigger, to consider the Fcc lattice as a cubic lattice with 4 atoms in the cell and use as unit cell the cube that corresponds to the cubic Bravais lattice. You see what I mean? Okay, I will repeat it now because I will now discuss these 2 lattices and you will see. So the answer is, for a given Bravais lattice, this is what one tends to prefer. Okay, so now let me go to 3 dimension, which is more complicated, and you will see what I meant. Okay, so let's look at 3-dimensional cases now, and I want first to discuss the case of the Bcc lattice. So let's draw lattice point, or some of the lattice point. So I'm considering the Bcc lattice. I can, a first definition is a cubic Bravais lattice with 2 atoms in the basis. This is one way to define the Bcc lattice. So I draw the cube of the cubic lattice. So there are atoms at the corner of the cube, and there is an atom at the center of the cube in the Bcc lattice. Oops. Here I put the okay, so these are points of my Bcc lattice, and as I was saying, the first definition of the Bcc lattice is that it's a cubic lattice, a cubic Bravais lattice. With 2 atoms in the basis. Okay, so here I have drawn unit cell of this cubic Bravais lattice, and it has 2 atoms in the cell. So this would be the conventional unit cell, that is the unit cell for the cubic Bravais lattice, and it has therefore 2 atoms in the cell. So it has the atom at the center and 1/8 of each of the corner atoms, so 2 atoms in the unit cell. Well, yes, the corner here would have a factor 1/8 because one would count them 8 times. But I think it's pretty obvious. Okay, so associated with this cubic Bravais lattice, one has as a possible corresponding unit cell, which is the natural, the obvious, the simple, symmetric, whatever. Symmetric, cubic unit cell. And it has two atoms. Per cell. So this is the conventional. So this is the conventional unit cell. It's the simplest one can imagine, and it's associated with this definition of this view of the Bcc lattice as a simple cubic lattice with two atoms in the basis. Okay. Now, of course, we know the Bcc lattice is a Bravais lattice, and therefore there is also a possibility of having primitive vectors with just one atom in the basis. So the Bcc lattice is a Bravais lattice. So this is the second view with, for instance, as primitive vector the three vectors that would be two of the edges and the vector that brings to the central atom. So E1 is equal to A0, 0. E2 is equal to 0, A0, and A3 is equal to A over 2, A over 2, A over 2. So my side here has a length A. So I would have these three vectors. This would be A1, this would be A2, and this would be A3. These three vectors would be a good choice for primitive vector of the Bcc lattice. And associated with these three vectors, I can construct also a unit cell that has one atom in the cell. So this unit cell would have as basis the base of the cube. So the area included by the unit cell defined by A1 and A2 as x1, A1 plus x2, A2 with x1 and x2 between 0 and 1. So this would be the basis. And then it would have a side, one of the side would be here. So this is would be a front side, and then there would be these vectors going like this. Oops. So it would have another here. Okay, this is the front, this is another here, and one would be here. And then some place like this. Well, you see that it's not an easy object. So this object would have here. Okay. Well, it's a parallelepiped that would have one face here, one back face. Yeah. Yes. It's not easy to do. Because, yeah, okay. Alors, this is the base, and then I need 3 vectors that go like this. So, 1. Okay. Start again. Oops. Okay. Now I have a vector here. Face towards atom. Okay. So I have this face in the back. I have a face here. Now this one goes like here. This one goes up like here. This one goes up like here. Maybe I don't go too high. And okay. Good luck. Okay, so it's something like this. That would have this as a bottom face, this as a top face, and then this side. You see that it's not a simple object. So the unit cell of the Bcc lattice that would be have as edges these 3 vectors A1, A2, and A3 is a complicated object with the vector A3 that is not perpendicular to A1. It's not easy to see and it's not easy to draw, but it has 1 atom per unit cell. So this is just to tell you that the primitive cell of the Bcc lattice, if one tries to draw it from some primitive vectors, like these 3 primitive vectors, is not a simple object.
Insofar as they define?
Yes. It has the base are squares, and then it has the angle that corresponds to the diagonal of the cube, and the top face is also flat. I mean, it's also a cube. It's also a square, sorry. And yeah. Okay, so this is just a bit in answer to your question. This is certainly not a very convenient choice of unit cell to define this one. Okay, so one can look now at the Wigner-sized cell. So the conclusion here is the conventional cubic unit cell is simple, but it has 2 atoms in the cell, and normally the primitive cell of the Bcc Lattice is a complex object. Of the Bcc lattice, the same would hold for the Fcc lattice. The shape of the unit cell of these Bravais lattices, if one tries to construct them from 3 vectors, A1, A2, and A3, like I did, has a complex shape. So normally complex unit cell with 1 atom per cell. So this is what I tried to draw. Instead, the Wigner-sized cell, which is not defined from the primitive vector, but from the definition I gave you before. So the Wigner-sized cell is a more symmetric and understandable object. It is, in the case, I will show it to you, it's a truncated octahedron. So, I wanted to show you now. See if it works. Maybe. It moved here. Okay, it works. Okay. Maybe. Okay, so this is the Wigner-sized cell on the left of the Bcc lattice. So it's a truncated octahedron. You can see 8 hexagonal faces that face the first nearest neighbor of the atom at the center. So there is an atom at the origin, and the Bcc has 8 nearest neighbors, and you can see this hexagon which face the 8 first nearest neighbors. So these are essentially the bisecting plane between the central atom and the first nearest neighbor that give rise to these 8 hexagonal faces. And then on top, on bottom, and on the 4 sides, you can see these square faces which face the second nearest neighbor. So in the BCC, you have 6 second nearest neighbor, and so you have these 6 squares that are the facets that face the second nearest neighbor. So the octahedron, which would correspond to the plane of the hexagon, is truncated 6 times, putting this square facet that face the second nearest neighbor. So in the case of the BCC, not only the first neighbor, but also the second nearest neighbor need to be included to limit the volume of the Wigner-side cell with bisecting plane. So this is the Wigner-side cell of the BCC. So to finish here, it's a truncated octahedron which has 8 hexagonal facets. It's hexagonal facet that face the nearest neighbor, facing the nearest neighbor, and it has 6 square facets that are facing the second nearest neighbor. So this is the case of the BCC, and again, the symmetry operation that transforms the BCC lattice into itself. For instance, the reflection in the horizontal XY plane that would transform the BCC lattice into itself also transforms the Wigner-side cell into itself, and the rotation about the C-axis, the vertical axis, rotation by 90 degrees, for instance, that would also transform the BCC lattice into itself, transform the Wigner-side cell into itself. So it's a very symmetric object, and it's a uniquely defined unit cell that doesn't depend on the choice of the primitive vectors, and is convenient. It's not as simple as the cubic cell in the representation of the BCC as a cubic Bravais lattice with 2 atoms in the cell, but it's the simplest one can get, and the most symmetric one can get with just 1 atom per cell. Okay, so BCC and the FCC is what you have to the right. So the Wigner-side cell of the Fcc lattice is this object, which is a rhombic dodecahedron. It has 12 equivalent facets that face the 12 nearest neighbor in the Fcc lattice. So in the Fcc lattice, it's enough to look at the first nearest neighbor and the bisecting plane to get the full Wigner-side cell. No need to look at the second nearest neighbor. So to finish, just writing down what is the Wigner side cell of the Fcc lattice. We have seen the Bcc lattice. So just to summarize, the arguments are the same. Similarly, excuse me? No. For Fcc lattice, I will use my capital. Similar for Fcc lattice, so the Fcc lattice can be seen as a cubic lattice, Bravais lattice, with 4 atoms in the cell, in the basis. And the corresponding conventional unit cell is a cube with 4 atoms in the cell. Four atoms per cell. If one instead looks at the Fcc Bravais lattice, so a lattice with 1 atom per in the basis, then the primitive cell is in general a complicated object, like we have seen for the Bcc lattice. The primitive unit cell with 1 atom per cell is not very symmetric, is a complicated object. In general, while if one looks at the Wigner side cell, okay, I also made copies so you can have it for your notes. You can pass it. So the Wigner side cell instead in this case of the Fcc is a rhombic dodecahedron. A rhombic dodecahedron. So it has 12 rhombic facets. That face the nearest neighbor. That face the 12 nearest neighbor. Okay, so I will just turn this off. Okay, so the simplest is either to consider this Bcc Fcc lattice as cubic Bravais lattices with 2 or 4 atoms in the cell and use the cubic unit cell, which in the cube as unit cell, or consider them as Bravais lattices with one atom per cell and use the Wigner-side cell. So that I showed you. Okay, so that is for the Bravais lattices in real space. So in the next part I will introduce the reciprocal lattice. So this is the real space part. And now we introduce the reciprocal lattice. So, reciprocal lattice. Which is useful, for instance, in crystallography, where the reciprocal lattice vectors are the Bragg vectors. So, but also, as you will see, in solid-state physics, for the description of the Bloch state, we will use the Wigner-side cell in the reciprocal space, which is the Brillouin zone. So this is also very important. So, okay, let's consider define the reciprocal lattice. And for this, we are considering an initial Bravais lattice in real space. So consider a Bravais lattice that corresponds to a set of points R. So this is my Bravais lattice. And I consider also plane waves. So I consider Bravais lattice and I consider plane waves. So the plane waves are objects like that. F of r is equal to exponential I j r. And in the direction of the g vectors here, j, there is a periodicity, that is the periodicity is given by, it has a periodicity lambda, where the norm of g is equal to 2 pi over lambda. So plane waves are objects that have a periodicity along the direction of the g vector, and this periodicity lambda is 2 pi over the norm of this vector j. So I have these things, the Bravais lattice and all the plane wave, and now I'm asking the question, what are the G vectors that give rise to plane waves that have the full periodicity of the Bravais lattice? So I'm asking the question, what are the ensemble of the vector G, or what are the G vectors such that with these such G vectors, the plane wave have the full periodicity of the Bravais lattice. That is, f of r is equal to f of r plus capital R, where capital R are all the possible R vector of my initial Bravais lattice. So here I'm considering the translation. I'm translating my plane wave, and I obtain the same thing, the same value, and I'm asking that this is valid for all R vectors of my Bravais lattice. So I have plane waves, and I'm asking what are the J that give a plane wave that is periodic, that has the full periodicity of the Bravais lattice. Okay, so, well, this is a mathematical question, so this is my question. And if I impose that my plane wave have this periodicity, so exponential I j times r is equal to exponential I j times r plus a Bravais lattice vector, any Bravais lattice vectors, then I obtain that exponential I j capital R must be equal to 1. And this, I want it to be true for any vector R belonging to my Bravais lattice. So I impose that for any R vector of my Bravais lattice, the plane wave must be periodic, must have that periodicity. So it must have the full periodicity of the Bravais lattice. So if I'm imposing these conditions, this means that J times R must be equal to 2 pi times an integer. And this condition actually defines the reciprocal Bravais lattice. That is, the reciprocal Bravais lattice are all the J's that verify these conditions. So the definition we can define the reciprocal Bravais lattice well, I didn't say yet, it's a Bravais lattice. So the reciprocal lattice of a Bravais lattice it's the ensemble of all the G vectors such that exponential I j times R is equal to 1 for any vector R in my initial reference Bravais lattice. So this is the definition of the reciprocal lattice of a Bravais lattice. So basically, it's all the G vector that give plane wave that have the periodicity, the full periodicity of the Bravais lattice. Okay? All right, so now there are some properties that I would like to give you concerning the reciprocal lattice, and the first one is that it is also a Bravais lattice. The reciprocal lattice of a Bravais lattice is a Bravais lattice. So, it is and in fact, it is a Bravais lattice that can be generated with three primitive vectors, which I will give you. So, it is a Bravais lattice, and it is a Bravais lattice that can be generated by the primitive vectors B1, B2, and B3, given by and then there are two equivalent ways to give them. The first one is that Bi times Aj, so A is the primitive vector of the initial Bravais lattice. Bi times Aj is equal to 2 pi delta pi j. So this is a first way to give these three vectors. And the second way, which is equivalent, oops, I'm not sure. Okay. And the second way is by giving them explicitly, and this would be B1 is equal to 2 pi A2 cross A3 divided by A1 times A2 cross A3. So the denominator is the volume of the unit cell in real space. And then one has the cyclic permutation. So B2 is equal to 2 pi A3 cross A1 divided by A1 times A2 cross A3. Sorry, it's a bit crowded. So this would be for B2 and B3 is equal to 2 pi A1 cross A2 divided by A1 times A2 cross A3. So, sorry, so this would be the table that gives B1, B2, B3. So this is the second way to give these three vectors, and they are equivalent. So I mean, it's easy to show that if one has this, one has also this. So in this direction, it's simple. That is, if I consider, for instance, B1, if I multiply by A1, I will just obtain 2 pi, so it works. And if I multiply B1 by either A3 or A2, for instance, if I multiply B1 by A2, I obtain 0 because A2 plus A3 is perpendicular to A2. And the same for if I multiply by A3 B1, I obtain 0. So this is fulfilled in this direction for sure. By cyclic permutation, one has the same for the other two. B2 times A2 is equal to 1, 2 pi, and B2 times B1, A1 is equal to 0 because A3 cross A1 is perpendicular to A1. So this is fulfilled in this direction. And then the other, the equivalence is just that because B1, B2, and B2, 3 are unique. If one has linear independent A1, A2, and A3, this condition tells you that, for instance, B1 has to be perpendicular to A2 and A3. So B1 must be perpendicular to the plane that includes A2 and A3. So its direction axis is well defined. B1 is the direction of B1. The axis is unique, and its norm and direction is also unique because B1 times A1. So the projection of B1 on the vector A1 is equal to 2 pi. So its norm and its direction are also well defined. So it's unique. It has to be perpendicular to A2 and A3, and its projection on A1 must be 2 pi, so it's uniquely defined. So these two definitions are equivalent. Okay? All right, so these are the vectors that generate the reciprocal lattice. Well, this is what I claim. So first, one has also to have that B1, B2, and B3 are linearly independent in order for this to work. So B1, B2, and B3 need to be linearly independent. And this actually I will ask you to show it yourself as homework. So I ask you to calculate the determinant of B1, B2, and B3, and show that it is equal to 2 pi cube divided by omega, where omega is the volume of the unit cell in real space. So if it's non-zero, this means the 3 vectors are linearly independent. So I will ask you to show this. So the homework is to calculate this, which is the volume actually of the unit cell in reciprocal space. So I ask you to calculate the volume of the reciprocal space unit cell, or the reciprocal unit cell. So, in other words, to check this. And you can rewrite it actually as B1, which is the way you can evaluate it, times B2 cross B3. So, using this definition, you can calculate this, and it's useful to have also some rules concerning cross products. So in particular, you can use this relationship A cross B, general formula. So A cross B cross C is equal to B times the scalar product A times C minus C times A times B. So this is a general equivalence. So A cross B cross C is equal to B times the scalar product minus C times this scalar product. So you can use, while you will evaluate this, you may need this to obtain the results. So this is what I'm asking you to do for next time as homework. And then we will continue on to prove that indeed with this vector B1, B2, and B3, one has a Brave reciprocal Brave lattice.
Are you telling us to calculate the omega?
The omega is the volume of, I should have given it to you, yes.
It's the one you're telling us to calculate.
No, it's the volume of the unit cell, sorry. Omega is just E1 times E2 plus E3. So it's just the volume of the unit cell. Sorry, I forgot to.
So we are going to use that sub-identity. I don't see it similar to that.
Well, B1, B2, and B3 depend on this omega.
Okay.
Okay? Well, okay. This is the homework. And yes, we will continue next time on the reciprocal lattice and show that indeed this B1, B2, and B3 generate the reciprocal lattice. And that, therefore, it's a Brave lattice. Okay. Any question? Everything clear? Yes, you know? All right. Let's stop.